So this is the fourth in a series of lectures we're giving here. And this one is on exponential complexity of wireless test. As all of you are probably test engineers, and you know the different types of tests we do. So initially, we want to know what is our maximum performance. We have new generation chipsets, 11AC, Wave 1, Wave 2, AX. What can we reach? This is the marketing part of the test. And today in the Octobox, we can reach over 1 gigabits per second over the air. This is very nice. But this is a contrived test. We all know this is a test where there's no noise, there are no impairments, antennas are lined up just so, and we show the world the technology can do it. Now, what happens in the real world is quite different because you get hit with path loss, multipath interference from your adjacent networks, from all kinds of stuff in the nicest bands, baby monitors, phones, radar, and then a lot of variables kick in at the same time. And so some folks actually go, and traditionally we used to go from this maximum performance test. Now we want to know how well we do. We go right to the real world and we do design verification there. Now that's the worst thing to do. And today we're going to discuss why this middle step, design verification, is extremely important. And we're going to show how the Octobox can be used to systematically change one variable at a time, test these complex adaptation techniques that are in the modern wireless products, and how to avoid disaster here. So the more we do here, the less we need to pull our hair out in the real world. So this is the most basic adaptation, goes to the beginning of time in .11. And of course, this is rate adaptation, or MCS, modulation coding scheme. So this is a plot we did with our PAL device. PAL, by the way, stands for, it's basically a partner. It doesn't stand for anything. It's not an acronym for a change. It looks like this. We have it up there. We have a bunch of modules. So our platform basically consists of boxes and modules. And this device, we're going to show you several things it can do during the demos. And one of the things it can do is be a partner. It's highly controllable. It's based on a real chipset. And it can also be a test instrument, as well as a real station or AP or multiple stations. So in this case, we set it to fixed MCS, which you cannot do with a real device, but we can do with a PAL. And we ran a throughput versus range test. So you can see here with MCS 9, up to this point, we get nice throughput, and then it drops precipitously. So at this point, we really our device should transition to MCS 8, because with 8, we are getting higher throughput, and so forth. The best time to transition is along this outer upper perimeter of the wave, right? So this is where we expect our device to transition. But many times we see the devices, they would just cling to this MCS 9 or MCS 8, and they don't adapt in time. And so what we can see is a big drop in throughput like this until the device recovers and decides, okay, now I can transition. And so this is one example of such a throughput versus range plot. It's a courtesy of smallnetbuilder.com. And they are basically running, we suspect that's what happened, is we probably didn't adapt. This is versus path loss in the Octobox platform. And there was a drop in throughput, and then it recovered. So we need to monitor the adaptation techniques to figure out why this happened. And the PAL also is a monitor, so that's another thing it does. And we'll show you how we can zoom in and look under the hood and see what is the cause of this. Now, SmallNet Builder used to test at these discrete points in the house. And if you do that, if you insist on kind of going from this test exactly to the real world to do your device verification testing, this is one example of why that's not a good idea. Not only do you have a lot of uncontrolled variables, but you're going to miss stuff. Because if we tested these 2 points, we're missing this adaptation problem. Okay, so what we're going to do next is we're going to run a live demo using the PAL as a partner. Our demos looks like this. We have, this bunch of modules up there. Jamin's going to configure one of our PALs as a monitor, so it can show us some detail of adaptation, and another as a traffic endpoint. So this is going to run iPerf. It's going to connect to this Netgear AP inside, and we're going to run our throughput script, which will step the attenuator by 10 dB. So we're making core steps right now just to make the demo fast so you guys don't go to sleep. But of course you can step by 1 dB or even half dBs and dwell longer on each point. So what we have here is this PAL. All of our modules are controllable in the browser. And all of these controls are also available to automate via API. Every control is available for automation. So we have a bunch of these instruments here, and we're going to click as we need to reference them. So right now, we have this PAL configured as a station. We can also make it access point. It's associated to the access point where in this 80 megahertz channel, 153 is our primary channel. And we are basically telling it adapt as normal, be a normal client. Don't do anything fancy. If we wanted to run fixed MCS, we could pick an MCS, but we're not going to do that here. We have 4 streams. It's a Wave 2 device. And that's what we're going to run. Okay? So Jamin, you're going to start a test. And so our script will then start a test, and it's going to run throughput and step by 10 dB. We're going to go into the monitor. So this PAL, the second PAL, is a monitor. So right now we're running real time. So these parameters, we are watching real time. So RSSI, as I mentioned, it decreases in steps of 10 dB. And we're really trying to run a very fast test here. We have 4 streams in the air, over the air. You guys can look inside later. And okay, so here some adaptation starting to happen as we're dropping the RSSI. This is our MCS. It's also starting to adapt. Bandwidth is holding steady right now, but data rate is dropping as we're dropping the RSSI. So even further, even the bandwidth here adapted. So you can actually put these plots together with throughput and get a lot of information that you wouldn't otherwise get. Okay, so this is the demo of how we run traffic, how we can get plots like this inside the Octobox, and then we can torture the device. We can also add interference. Interference is very important because in the real world, you come to the real world and in an apartment building especially, lots of neighbors, you will see 30, 40, 50 adjacent networks. They're in range. Your neighbors may be running video. They're streaming video to their set-top boxes. And this is pretty aggressive interference. And so another module we have is the iGen. So I have one here. And we have it up there in the pile of our modules. The iGen can do 2 types of interference. It has also a real chipset, which we can control in the driver and firmware level. And we can play traffic. We can generate traffic interference. And it can also monitor, just like we saw right now with the PAL monitoring. The iGen can also do that. So you can use them interchangeably. But it also has a frequency synthesizer built in, and it can generate waveforms. Waveforms like radar, Bluetooth, baby monitors, and so forth. We have a built-in attenuator so we can control the level of interference. This is the iGen tab here. We're on the traffic tab right now. This is the waveform tab. We'll come to it later. This is the monitor tab. So these are the 3 tools that the iGen gives us. What we're doing is we're replaying a PCAP file. This is a Wireshark capture. They're standard files. And we're going to replay. We can loop through it. We can set priority of replay. And including all of our devices, PALs and iGens, they can also be set to not do backoff, not do contention. Just stay, and this is very aggressive traffic. Okay, and then we can control the gap, attenuation. We control gap between packets. That's how we control the channel congestion. Okay, so what we're going to do is, Jamin, we're going to start traffic running, and then we're going to hit one of the channels, sub-channels actually, with interference. And this is just one example. This is co-channel interference. And so we're basically monitoring, we're still at a good, 4-stream, nice high RSSI. We're not doing anything funny yet, or maybe you are. So we're going to go and start, and we'll let the iGen configure itself. So what we're doing here, we're injecting interference into channel 161. Okay, so now you can see we're actually injecting traffic into one of the 20 megahertz subchannels, and the bandwidth got adapted to 40 from 80. Okay, we had it start at 80, and now because we injected into one of the higher 20 megahertz channel, it adapted. So this device behaves as we expected. So another thing I was going to show you is the synthesizer and the types of. So actually, I'm using TeamViewer here, just so you guys know. TeamViewer into Jamin's console. The test console. Okay, and so the other, so now we have LED, so it's running traffic, but I can also run waveform interference, and here we have all kinds of interference radars. We can define pulse waveforms on and off, Bluetooth, low energy. We can define custom Zigbee or custom profiles, frequency sweep. So these are all, these files that we use in the iGen. We have in the iGen and PAL, we have the same file system, and you can drag and drop your own patterns. So we have captures. These are PCAP files we preloaded. You can get your own, and the waveform files are in CSV format, so they're easy to customize if you need to, and so you can create your own custom patterns and replay them as well. So just so we have different radar types. These are pre-configured, but here we can just select, and we can select custom profile, and then we have to go and select which CSV file. So that's what this guy does. The iGen, it lets us create all kinds of interference. We can have multiple of them in the system at different levels. We can automate the traffic levels. We can sweep through different traffic levels, turn on and off. Video streams or whatever we need, whatever we pre-recorded. So the nice thing is you can pre-record, say, video traffic. You can put something in the Octobox, pre-record, and replay whatever you need, whatever type of traffic you need. So in summary, these are the key impairments we find in the real world. Obviously, path loss, multipath, interference, and motion. All of these we can control very finely with our modules. And our system is completely isolated. You should not see any other stuff in it, like in some cheap boxes you can get. But this is fully isolated. If you'd like more details, we have them afterwards. Obviously, interference is one important thing, because this is what makes us adapt. You saw that channel adapt, and what happens if your device doesn't adapt, doesn't throw away that channel that was congested, that sub-channel. Then your performance goes down. So these adaptation techniques, they're complex. It's all new code. You have different revisions of code, and you need to automate these tests to keep retesting as your firmware and your driver are refined. And so this is what we designed this test bed to do. So we can do co-channel, adjacent channel interference. We can replay different applications or even run them. The PALs are Linux devices. And some of our customers have a login, and they can run their own video streaming or whatever they need to run as traffic. Okay, another pretty new type of adaptation. So we're just kind of going through some examples of adaptation. We're obviously not going to hit them all. And this is band steering. How many of you folks are testing band steering today? A few. Good. So this is new technology. So what I'm going to do, we have this ACES router. This is its menu for adaptation, okay? And you can see that this is fairly complex, and what band steering is essentially a router can have, let's say, 100, sorry, not 100, say 20 clients in the 2.4 band. A lot of clients would just like to go to 2.4, and maybe 3 and 5. Or maybe they have in the 5 gigahertz band, they say 5 gigahertz is our fast lane, it's our fast band. We don't want any slow devices that sit across several walls, because now they've dropped down to low rate, and every packet takes them that much longer to get on and off the air. So they're occupying the air link, they're making everybody slow down. So some devices they will want to throw from 5 gigahertz band to 2.4, some devices from 2.4 to 5, and this is a load balancing technique. And how is the decision made? So there are a lot of parameters here. For example, load. This is the bandwidth utilization. Okay, we can set it. We have RSSI level. We have RSSI level threshold. We have phi level threshold we can adapt. So if you are, let's say, below some phi rate, we don't want you in that 5 gigahertz band. Okay, we want you to go here. And so you can see how complex, and we need to test this software for these new APs. How do we test all these decisions that are made? So one way we do it is we can use the PAL, and the PAL is highly controllable. We can actually set it to any data rate. It could be a client, and we can set it to any, let's say, ABGN, and we can set it to stations. We also have multi-station. We can have virtual stations. We can set its channel width. We can set its guard interval. We can set its MCS. So if we want to set it on low MCS to be kicked over from 2.4 to 5, we can do that. Any primary channel, including 2.4 gigahertz and 5 gigahertz channels, you can just select whichever channel we need. So the iGen, the PAL, when it's in AP mode, I'm going to put it back into the AP mode, it can also generate load. So what you see is all of these thresholds, we can actually control the traffic to exceed, to be on one side or the other of the threshold, including bandwidth utilization, MCS, RSSI we control with our attenuators, which are also here in the tabs. And so we're going to go back to PAL1. So what I'm going to do, so right now we have, I can't see, my eyes don't work. What is this congestion? 90. Are we running anything, Jamin?
Yeah, it's up right now, so it's 90%.
Okay, so Jamin started it. So what we're doing, we are replaying this file, okay? And what we told it to do is zero minimum gap between packets, okay? And we told it to, the priority, we set it, so the priority WMM tells you how aggressive this interference is. Background is not very aggressive, but if we want to be really aggressive, we can set it to just be a jammer. No back off. You should never put antenna on and transmit it, because it's a very powerful jammer. So Jamin right now has it at a high utilization, but of course we can control utilization. For example, this is a low data rate, so each packet takes a long time to get on and off the network. If we change, for example, MCS to something faster and update, it will drop that load. Or if we change packet gap, so I have to hit update, and then it just takes just a few seconds for us to reconfigure the chipset, and then it will change the load. But again, so one nice thing about this replay mode is it's generating, it doesn't need a partner device. It's not an AP and it's not a station. It's basically a replay device because we control the firmware of this chipset. we can tell it, you just replay device at this point. So, okay, so with the faster MCS, you see the dramatic change in the load. It's much less right now. So let me put it back to something more interesting, and I can change the channel width. I can change, for example, the gap to say 300. Now I have very fine control of the percent load and update, and then it should give us some high utilization percentage. But the point is we can control it in different ways. We can set up different types of traffic. It doesn't need another device to associate with, and at the same time, it's also an access point. It will associate clients, and it will replay the load. So I don't know what I did to it. I must have done something, but we'll get back to it later. Okay, so when we're talking about band steering, and we're going to talk about roaming a little later on, there's some important amendments to Data 2.11 standard RKV that are just now getting deployed. Now, how many of you folks are working and deploying these? Okay, a few of you. So they are coming, our customers tell us they're coming, particularly for enterprise. So 11R is a fast roaming standard for the enterprise, designed basically to support voice. So we need very fast handover for voice. 11K is the radio resource measurement, and it's designed to monitor the physical layer of our Wi-Fi network, monitor RSSI, loading, all those useful things, activity. And 11V is wireless network management. So this is measurements and this is management. And so 11V relies on the measurements, but now 11V can control. So it can tell devices, go hand over to this AP or that, go switch to this or that band. So we have a lot of control over the clients. So we're going to kind of finish up our introduction, this long drawn-out introduction. Some people tell me it's way too long, but okay. What we've looked at, why did we call this exponential complexity? And the reason is every test you have to do, say throughput, which is a very basic test, it relies on range, orientation, multipath, interference, a whole bunch of stuff here for interference scenarios, load, frequency, obviously, how many devices, and etc. So each test that we add, for example, we add 11AC wave 2, we add 11AX, we have all these modes, we have different channels. We have to go through a series of important tests. Now we are adding load balancing and meshing, which we're going to talk about. You have to run them across some respectable number of variables. You cannot do this one at a time in open air in the house, because in the house you're getting hit by a lot of variables uncontrollably. Even if you have a house somewhere outside and there is no traffic there, you will have uncontrollable multipath, and you cannot really easily, for example, change velocity of motion, different patterns of motion. It takes too long. And you cannot properly test. It takes too long, and it's uncontrolled, and you cannot record your detailed results either. So that's what we do for a living. We give you a platform that can do this for you. It's compact. You can wheel it to your bench or even in your cube, and there's a lot of capability. So this is kind of the outline of the rest of the seminar. We're going to look at new technologies. Oh, we're even doing well on time. That's great. So 10:30 to about 12:30. We're going to look at the new technologies, obviously AC, Wave 2. We're going to look at AX, look at what the difference is between OFDM and OFDMA. For AX's OFDMA introduces a very new access scheme. Beamforming and mu-mimo. Then we're going to look at some meshing technologies, and then roaming, of course, goes with meshing. Once you have deployed a number of APs, well, you've over-provisioned your coverage, but you still depend on the clients to hand over to the AP that's closest to you. Then we're going to take a short break. We're going to talk about coexistence and recommended practices document, which could be useful. Okay, so we're going to dive into this first bullet. And we start with the summary. I'm not going to read all the numbers in this busy table. Andrew, thank you for putting it together. But basically, it shows you all of the standards of IEEE through AC, Wave 2, and AX. And you can see that, we have modulation, spread spectrum techniques, coding rate, number of streams, channel width, guard interval. You take all of these variables, you plug them into a formula, and you get data rates. And you can see how many different choices you have. So these are all adaptable. And the chipset needs to pick one of them for each cell. And so there are many, many data rates that you can end up with different combinations. So you can see how complex this adaptation is. So today we have 11AC Wave 2 is our latest technology. It uses OFDM. It goes up to 256 QAM. Our highest data rate with 4 streams is 3.5 gigabits per second. For 11AX with 1024 QAM, OFDMA, now we're going to discuss this in a second. The channels here, we're stepping up to 80 plus 80 or 160 megahertz channels. So 80 plus 80 don't have to be contiguous. 160 is contiguous. And so we're getting a very big step in highest physical layer data rate here. But of course, a lot of data rates in between, depending on path loss, multipath, interference. Okay, so diving in OFDM and OFDMA. So obviously we all know OFDM. We're all by 5 people here. Orthogonal frequency division multiplexing. We have a number of subcarriers. Whenever a station grabs the air, it uses all of them. Very simplistic. There is CSMA-CA contention on the air. One station grabs the air at a time, station or AP. Now, 11AX is introducing OFDMA, orthogonal frequency division multiple access now. Now, multiple access means we give groups of subcarriers to different stations, and this is uplink. So APs usually have the highest throughput. They have the highest number of streams, antennas, but stations can be a phone or a pad, a sensor. They're usually slower. And so they don't need all of these subcarriers. They don't need all that bandwidth. And so we can assign them in the different subsets of subcarriers we call resource units. And they can then be on the air link simultaneously. So this is their frequency sharing. And just for information, LTE has done it first. And OFDMA is more complex because they have a time dimension, because they are working with mobile phones that are driving around and switching from base station to base station. So at different points in time, different frequency slice can work better for even the same station. So they hop these, they call resource blocks, we call them resource units. They change them dynamically versus time as well. So 11AX, so how do we stay backwards compatible? All the 11 technologies are backwards compatible. And the way we usually do it with any new technology is through preamble. And the preamble has to be understandable by all the legacy stations. And same thing with 11AX, it takes the entire channel. This is frequency here. So say 80 megahertz. We're showing it this way as well. And we're just taking up the whole, and by the way, National Instruments contributed this, and Chris is in the audience who did this slide as well. Thank you very much. And then after the preamble, in the preamble, obviously, we announced TXOP, how long the station is going to be on the air, all the necessary contention parameters that all the stations need to hear. And then after preamble, each station grabs its own slice of spectrum, its own resource unit, and uses it in parallel. It's pretty neat stuff. Okay. So, okay, so this is our OFDMA. So why do we do it? We want to scale network capacity. So this is all about scaling. And the way we scale is we take a bunch of stations that can be slow, we put them on the air at once. That means each slow station doesn't have to transmit one at a time. Another way to scale is spatial multiplexing, so in space, where we actually form a beam to each station. That's multi-user MIMO, mu-mimo. That's available today. And so typically the stations, AP stations, all the legacy devices they have omnidirectional transmission for most of them. So they transmit in all directions, and only one can be on the air at the same time. So we cannot spatially have them together, transmitting together. And they have to use the CSMA-CA contention protocol to figure out who is on the air. But for mu-mimo, we have beamforming technology. So now with lots of antennas on the access points responsible for doing channel sounding and figuring out how to take that omni energy and focus it in one direction or three directions simultaneously. So beamforming is actually a subset of multi-user MIMO. Beamforming is done for one station and one AP. So if we run just a beamforming test, this is some results we collected in the octobox. You can see the gains. This is throughput versus range. And you can see when we turn beamforming on, just because we're directing all the energy at the stations, we get higher throughput. We have better performance, even just with one station. Okay, and with multiple devices, the way we do beamforming in the octobox is we spread antennas around the device. So you have 360 degrees around the device. The way you do beamforming is you have to make them decorrelated. That's a technical term, but that means their angular spread is as wide as we can get. That's what gives us maximum gains. Okay, so if we have three stations, we're going to spread them 120 degrees apart, and we have very nice ways to adjust our antennas, and we can do that. Another thing to keep in mind is we have groups of stations that may be close together, so they have high correlation, and there's no way to form two beams to them, so only one station out of a group can be on the air as multi-user MIMO client. But one station out of each group can be on the air, and these guys will do CSMA among themselves. And there's a protocol to pick who is on the air. So we're going to run a live demo. Our pals are multi-user MIMO capable. And these two pals, we used one as a monitor, one as a client, as a partner in traffic. So now we are going to switch them both to clients. And we have a path to this AP. So we are connecting them inside. You guys, during lunch or break, are welcome to come and see it. And we are using for multi-user MIMO only one chain. So right now, these devices are SISO. We can also configure the testbed for 2x2 for multi-user MIMO, but we're getting lower gains, and that's as expected. And even in open air, we get lower gains with mu-mimo where we use 2x2. So our demo is going to be a single chain. So Jamin, are we ready to go?
Yeah.
Okay. So Jamin has set it up. You see he has configured only one stream here. And he has enabled mu-mimo. And so with the first run we're going to do is with multi-user MIMO enabled. And we're going to use the chariot, and we're going to do our run, and we're going to record aggregate throughput of these stations, and then we're going to record each number, so the guys will tell me what they are, and I'll go edit them here with mu-mimo on and mu-mimo off, and then we'll compute this gain. Okay, so So that's kind of the signal path here. While Jamin is doing the run, I'm going to show you a kind of an expert mode of mu-mimo, where we have more stations. We can have some stations partially in one group, partially in another group, and we can virtually configure them flexibly around this access point under test. This is an expert test bed. And so it gets pretty sophisticated, but for typical tests, right now we're using 2 clients, so let's see where we are. Are you done? Okay, so what did you just do? Are you running again?
Yeah.
Okay, so we're...
First test it was beamforming, and this is the actual mu-mimo.
mu-mimo, okay. So we're getting somewhere in the 500s right now. We're gonna let it run through. We have a minute to run. This is X-Chariot that we're using here, and then we'll record the number.
Excuse me, question.
524.
Okay, so this is the test. Okay, so Jamin, what, 524?
For mu-mimo on.
Okay, so 524. Okay, and then with mu-mimo off, we're going to run again. And so what he's going to do is turn the mu-mimo off in the access point. And then we're going to run through it. Okay. So while he's doing that, so this is kind of finishes up our first bullet here, and we're going to jump to the extender and mesh type of testing. We're trying to go through very quickly, so if you guys have questions, we're going to take them in the break or at the end. We're happy to answer questions. You're welcome to look inside and play with the system. Obviously, we're just trying to show you examples of measurements, and there are many, many test cases that the system can be configured for. So he's reconfigured the AP, so now we have with mu-mimo off, and we're getting about half the throughput of mu-mimo on, which is as expected, because now each of these stations can only be on the air one at a time. So they have to share the air link, they cannot be simultaneous. So once this runs through, we're going to plug in the final number and calculate our gain. Okay, so here we have what, 271? 271. Okay, so 271. And someone give me the ratio.
1.93.
1.93. So we're very close to 2. This is very good gain for mu-mimo because we have a little bit of overhead, so it will never be quite exact. Okay, so again, I'm trying to rush through this. We'll take some time at the end. And the next topic is extender and mesh. Okay, as you know, many vendors now have multiple meshing APs that they deploy to get better coverage. How many of you folks are working with this technology? Okay, a few of you. I know some of you are under, confidentiality. You can't tell me, but this is a very big thing. Obviously, the idea is to get coverage. And so this is important to test. The traditional architecture, right? We have every AP, it has an Ethernet port in the back. They're all wired to something that goes out on the internet, to the Ethernet. But with these meshing APs, they need to be able, the traffic needs to be able to hop through some of these APs to get to one of them, which is the main one usually. In some cases where you have operator like AT&T, they deploy an AP plus some extenders, and then you have to hop to get to the outside internet. And of course the clients, they also need to be able to roam among these nodes. Another meshing technology is IoT. IoT, as you know, is wireless connectivity of sensors and controls. It's not necessarily Wi-Fi, it could be Zigbee, another source of interference. And One of the prominent ones, as you know, is Thread. We have Nest, Google Nest founded the Thread group. And again, we have a 3-node. 3 seems to be the magic number. Our Octobox, similar to that system against the wall, 3 boxes like that, is specified in their test plan. And this is a simple mesh SISO. From each box, we see the other 2 boxes. That's all. It's a full mesh of 3 nodes, and that's the test. And they have their own test plan. But of course, meshes can get more complex than 3. And the way we do a 3-node mesh is we can use 3 of these small. We just introduced box 18. They're the 2 top small boxes. And our instruments, right now we have them piled up there. We actually have a little support structure. We can just put them right and make you a nice compact test bed. This is a more extensive test bed. It has both mesh and high throughput and any mu-mimo support. But you can just take this part of it and use it. When we have meshing, they have to be self-forming, self-healing. The APs need to find each other. Throughput is a function of hops and a function of range. And of course, routing efficiency and interference is always there. And roaming. So we're going to talk about roaming as well. So this is an example, one test we did a long time ago. That's back when I had short hair. And we basically, it's a very simple mesh. We have 3 nodes, and we have a switch, RF switch, that we close and open. When we close it, these 2 devices are directly connected, and we're pinging. We're pinging from this one to this one, measuring the delay and request for the ping and response of the ping. And then when we open the switch, we actually have a tiny bit of leakage here, but the signal is horrible. And then we have a hop. So the right answer is for this mesh to go through this hop. But what does it do? Okay, so this is ping round trip delay. So when we close the switch, we got a nice 2 millisecond delay, quick ping responses. But when we open the switch, it goes through the hop. It's 12 milliseconds, which is normal. It should hop through that hop all the time. But very often it goes off and it finds this path and it goes off. This could be 30 seconds. I'm not kidding you. It's off the scale of this plot. I couldn't put it even in the picture. But these are very frequent interruptions. So this mesh is thrashing. It goes to this path that barely works because it wants to find 0 hop path. So this is going to destroy not only voice, not only video, but even your IP session can get lost with such a mesh. So obviously very important test. This is a 3-hop mesh. This is one way we can configure it. With this test subsystem mesh, TS is test subsystem. This again, we have a full mesh. We can fully control overlap among these 3 mesh APs. We use a PAL for roaming, and we can move this PAL around and see how this handover works. Okay, a more complex mesh could be 4 nodes. So we could set up, for example, a PAL or any station really, to communicate with the console. Let's say we run iPerf, but obviously you can run other traffic. Let's say we make this a nice path, so hops from 1 to 4 to 3. And then let's say we take this attenuator and we put it to 60 dB. This link is out. It's lost. So now the mesh has to reconfigure. It can go 1 to 4 to 2 to 3, or 1 to 2 to 3, or 1 to 4 to 2 to 3. So it has a lot of choices. And we can really torture it. We can set up conditions where more hops is actually better than fewer hops. And we can really test its logic. So that brings us to roaming, because roaming is very important, especially if we're going to over-provision these APs in a house now for consumers. So how do we test roaming? We have also a live demo here. Simple roaming test is with 2 APs. We can do it with more APs. So what we do is we basically ramp attenuators. So let's say we take attenuator 1, set it to 0 dB, attenuator 2 to 60 dB. That means this station will see AP1 and not see this AP2. But of course, we can make it see both and see whether it's thrashing or not. There are many test cases you can come up with. But a simple test case is when we bring it, associate with AP1, and then we take one attenuator, this one from maximum to minimum, and this attenuator from minimum to maximum. And that ramping, we can ramp at different velocity. At the same time, in this particular test, we again use pings, ping request to response delay, round trip delay, and we see where the transition takes place. In addition, we can use our monitor to monitor what's going on during the ping. So we can see the data rate transmission, loss of link, reassociation, and so forth. So it's a very powerful platform. So what we're going to do here, we're going to do a live demo. This is our roaming client, and we have yet to find a client that roams and without losing link. They all wait, they cling to their AP until it loses link before starting to scan and find another AP. So obviously this is not good for these meshing technologies because we don't want it to cling to its original AP once we walk 2 rooms over. And so the industry needs to get these clients better as far as roaming goes. So in this example, we have an AT&T AP, we have an AirTies extender, and these are the 2 attenuators that we're going to use. And then one of our pals is going to be a monitor. All right, so I'm going to go switch to the console. So this is our automated test. Attenuator 1 is set to 0, attenuator 2 is at 60. I click this button to roam. Okay, so I'm going to click it. And Jamin has a fast roaming setup. This is 1.5 seconds, in milliseconds here. And the ramping happened here very quickly. We told it to wait 2 seconds before it starts ramping, just so we get a baseline of pings. And then we told it just keep it going for 30 seconds so we can have everything settled in case sometimes transitions are long. They could take several tens of seconds. So these are parameters you can change. And so after 30 seconds, so we're pinging this client from a Linux server. We go to the Linux server and get the results from it. And so this is a fast ramp that we did. These are the ping response to delays. After it, you see it took a long time to hand over. So this is 2 seconds per division, 2, 4, 6, 7 seconds. So, and it only after it lost the AP. So this will definitely lose your session. And here we have some pent-up pings, so it changes scale on us. Okay, so now we're going to set it up. We're going to slow down the ramp, and we're going to turn on our monitor, and we're going to show you. So what Jamin is doing here is he's going to make this ramp time 10 seconds. And ramp delay also a little larger, so he has time to start the monitor after we kick off the room. And then the total duration a little longer as well. Okay, so we're starting the roam, and it's going to tick for 10 seconds, and Jamin's going to put the monitor on. And so we want to catch it before it actually roams. So you can see our MCS is 7 here. The phone is actually slower than the high traffic we were showing you. And bandwidth and data rate. And so what happens is now I think we have the roaming happen, and we're looking at it rises. I guess now we're up to MCS 9 and higher data rate. Did we already make the transition?
Yeah,
Jamin?
the
Yeah.
transition itself
is faster. Okay. So we're getting better signal. So let's go back to the roaming screen. And
Still depleting.
pardon?
Your RSI was still depleting, right?
Yeah, we need to kind of work around capturing it.
You are ramping, so the target should now be increasing.
Well, we're watching in the client chamber right now. So RSSI is from the client is steady. RSSI at the APs, we really need 2 monitors, 1 in each AP room, to see decrease and increase. But the client follows the AP, so whenever AP adapts a rate, the client follows it. So that's why RSSI is even. It's just where we're monitoring. So this means that more monitors, we can have more synchronized monitors and put the whole picture together to show you at different points. But again, we roamed, I guess the ramping was slower, and we transitioned here. Okay, so the next topic is coexistence. And of course, you guys know we have a lot of different standards trying to use the same unlicensed bands. We have Thread, which we've just looked at, that uses some form of Zigbee, not classical Zigbee. We have Bluetooth as a big interferer, or we interfere with it. And then, of course, the biggest culprit is LTE. There's LTU, unlicensed, and LTLAA. It will operate in the 5 gigahertz band. It's wideband technology. It's very aggressive. And what happens is when we have cells that are in range of one another, let's say you have an LTE E node B and an AP and with its own stations, depending on the overlap, they will step on one another. But more so, the LTE is likely to step on Wi-Fi. And because LTE does not do contention, it does not do CSMA-CA, does not do collision avoidance, it will jump in and it will transmit for periods of time without backoff. You can use, for example, our iGen or PAL to generate interference without backoff if you wanted to simulate it. And you can do the gap between packets to control how often it goes on. Now, the Wi-Fi Alliance, as you all know, is also developing a coexistence test plan. They're using our octoboxes to create these cells. So Wi-Fi cells, you have an access point and some clients. You have an E node B and some UIs. And then we have some very complex circuit between them to control. We can control coupling between any 2 boxes, basically, in their test bed. And they're testing a bunch of different protocols and what happens with different traffic patterns for LTE. So voice is vulnerable. Obviously, if you're running voice over Wi-Fi, what's most important is to have packets come at a regular interval. Now, on asynchronous networks like LTE, everything's scheduled. It's not a problem. You're in a licensed band. On Wi-Fi, of course, you'll miss some packets. But these packets, there's no throughput here, really. The packets are about 100 microseconds, 200, depends on coder, the codec, and with 20 millisecond gaps. But if you lose a burst of packets, you will hear clicks, your voice will be destroyed. So packet loss rate is an important measurement for that. And another important measurement is jitter, and that's variation in delay, propagation delay. So they don't arrive exactly when your decoder expects them. And so these anomalies can happen with aggressive interference from LTE. And of course, when you're roaming, if you see roaming delays, like what Jamin showed us of several seconds, you'll miss some voice for several seconds. So this is kind of a mission-critical application. And of course, you also have power consumption, sleep modes. There's a lot of extensive test cases we can define for this voice test. Okay, so IEEE recommended practices. So this is a document. I was actually one of the founders of this group. It was called TGT, task group for T was for test, we got the T. The document is .2. And it's not a standard, but there's a lot of work that went in by many smart people to define some test cases. And it's still very useful today. So we look at time-critical applications like we just saw for voice. For streaming video, if you're doing video teleconferencing, obviously voice is the most annoying thing to lose. You have high bandwidth applications like streaming video and time critical. And so the 802.11 specifies a whole list of different metrics and different variables, like we showed the matrix of tests and variables, and you can find them all in the standard. Overall throughput versus range versus receive power, transmit rate, antenna diversity, transition time, this is the roaming test, receiver sensitivity, this is usually run with fixed MCS. IEEE has guidelines on specific for each modulation coding scheme. It expects a certain curve for each MCS. So that's a good way to check the receiver. Multicasting, power consumptions, latency jitter, this is for voice packet loss, video performance, so all of these useful tests that we can run.